The next section talks about implication. So what is that? So we're going to talk about conditional connectives, the English equivalents of conditional connectives, converse, biconditional connective, order of precedence. This is really important. This is like PEMDAS. And then how this has implications in computer languages. So an implication uses this symbol here, right? This is read P implies Q, if P then Q, P only if Q, Q if P, P is sufficient for Q, Q is a necessary condition for P. There are lots of English equivalents for implication, and we call P our hypothesis and Q our conclusion. So why don't we go ahead and identify our hypothesis and our conclusion. So, Bill goes to the party only if Sue goes to the party. Okay, so Bill goes to the party is our hypothesis, and Sue goes to the party is our conclusion. This is written P only if Q. Next, Sue goes to the party if Greg goes to the party. This is a little different. This is Q if P. That means that our hypothesis is Greg goes to the party, see they're bolded, and our conclusion is underlined. Next I have for 8 to be even, it is sufficient that its square 64 be even. Okay, so this gives me P is sufficient for Q, right? Let's let this be our hypothesis, P, and this be our conclusion, Q. Remember, we call this implication symbol the conditional connective, okay? This is true when P implies Q is false only if the hypothesis is true and the conclusion is false. This is the only time it's false here, where our hypothesis is true and our conclusion is false. Otherwise, it is true all of the time. So let's determine if the following statements are true or false. And some of these won't make sense, but that's okay. So if Paris is in France, then the Louvre is in Paris. So this is a true statement, and the Louvre is also in Paris. So this is going to have an overall truth value. If the Louvre is in Paris, that's true, then 2 plus 3 equals 7. Is 2 plus 3 7? No, that's false. So this is going to have an overall false truth value. If 2 plus 3 equals 7, that's false, then the Louvre is in Paris. That's true. Well, false implies true gives us a true truth value, so here we have a true truth value. If 2 plus 3 equals 7, that's false. Paris is in Spain. That's also false. But here's what's crazy about implication. That gives us a true value. So when you need to put common sense aside sometimes when working with logic. So this is going to have a true value. Paris is in Spain only if 2 plus 3 equals 7. So this is false and false again. So this is still true. And you need to be careful, right? Because we can use this conditional connective to prove things that are really untrue. So the implication Q implies P is the converse or the opposite of P implies Q. It's important to note that if an implication is true, the converse is not necessarily true. So for example, the converse of the statement, if x equals -6, then x squared equals 36, that would give me if x squared equals 36, then x equals -6. Now this isn't necessarily true, right? Because what else could x equal? X could equal 6 or -6. So the converse in this case is not necessarily true. I tried to make that a -6, guys. Let's try that again. There we go. Not true. So here's a comparison of the two, right? If I have P implies Q and Q implies P, they're not necessarily identical because they have different values here and here. So the converse is not necessarily true. The statement form P implies Q and Q implies P is referred to as the biconditional, which we write as P double-ended arrow Q. And it's read P if and only if Q. Okay? So the biconditional is true only if both statements P and Q have the same truth value. So they both need to be true or they both need to be false. Otherwise, our statement is false. So why don't we go ahead and prove the biconditional? Because that's one thing that's really great about logic is we can make truth tables and prove things. So P implies Q, true implies true, which is true. True implies false, which is false. False implies true, which is true, and false implies false, which is true. Q implies P, now we're going the other way. True implies true, false implies true, true implies false, that's false, and false implies false, that's true. Now I use the and symbol. Remember, and is only true if both values are true. So that would give me true, because I'm looking at these two right here. False, false, true. And there we have it. Now, one of the final things I want to talk about is PEMDAS for logic. Remember, PEMDAS is parentheses, exponents, multiplication, division, addition, subtraction. It's typically called order of operations. But when we're working with logical connectives, there's an order called the order of precedence, right? And this is what we want to use. We're going to use negation, and, or, implication, and biconditional, okay? That's the first, that's the order in which we have to do them. Now, what's really nice is for PEMDAS, people have come up with sentences to help them remember. So, like, for example, please excuse my dear Aunt Sally. Unfortunately, this simplifies down to naob, which I don't think is really helpful. So if you can come up with a sentence that would help us remember this as a class, I would be much appreciative. So let's go ahead and do an example to put parentheses in place to show the proper order of precedence. So it's not, and, or, implication, biconditional. So the first thing I want to take care of is this not. So this is going to be not S and R. And here I have an and then last I have my or. So that's how we'd put in parentheses to show the order of precedence when the order of precedence is not given.